Well, warm welcome. Thank you for being here. Glad you're here with us today. Welcome back. If you've seen the previous two videos in the series, whether you have or not, get yourself ready with a notebook, grab a pencil or pen, whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we are continuing our series. This is the AP Calc FRQ Standards Practice Series, where we begin with some non-calculator questions, and then we'll finish the series with 3 calculator questions. These questions do not have the exact difficulty of the AP exam, but they do have the style. They're a little bit watered down in terms of difficulty, but in terms of the questions that they're asking you, that is spot on with what they would be asking you on the AP exam. So this allows you to practice the standards of how you would approach a problem, and then if you can replicate that process with harder numbers, you'll be fine. If you have any interest in tackling harder AP problems, you can check out other videos on my channel, but this is just to go over some standards. Okay? So we have a related rates problem here. Infamous related rates problems. I want you to practice. Give yourself about 12 minutes to work on this on your own first. And then when you're ready, come back, check out the video, see how we did it here. Okay, let's get started. It says water is poured into a tank in the shape of a right cone standing on its vertex. So let's get an idea of what that kind of looks like. Something like that. Okay, and the cone problems are infamous for the following reason. Cone has a volume equation with more than one variable in it. The volume of a cone is 1/3 pi r squared times h, which can get messy if we're taking the derivative of both sides because we have 2 variables there. And with respect to time, we'd have to do like a product rule with implicit differentiation. That's not how this is designed to work. So what I want you to notice is that the cone, which has a radius on its base, and it has a height which goes from the middle of that base. Let's see, I'll make it go sort of behind. That's our height. Those are always going to be in the same proportion, and this makes a right angle. Try to draw a right angle there. These will always be in the same proportion. So you can imagine that at any given moment, whatever the height of, the water or the oil, I think in this case it's water, whatever height the water level is actually at, this value x and this value here, y, those should be in the same proportion as the radius and the height. So we have to find the connection between those two in order to solve these cone problems. That's what makes these tough. Okay? So we're given information that will allow us to interpret the proportions of the cone. It says that the height of the cone is 120 feet and its radius is 24 feet. So now we have an answer to this. We have an answer to the proportion of the cone. I guess I'll just draw it on here. The proportions of the cone are 24 and 120. So we can say that h equals 5r. If you just make a proportion, you can do that too. You can say that 120 over 24 equals h over r, and then you simplify that, you get h equals 5r. So now we can use this to replace the h value if needed, or if we want to replace the r value, we can replace r with 1/5 of h. It just depends on if we're going to want our equation to be in all terms of r or in all terms of h. We'll figure that out based on the information they give us and also based on what questions they ask. Okay. The water level, that's our h. The water level in the tank is increasing at a constant rate. What did they just tell us? They told us the height, the water level is increasing. So they told us that dH dt is positive, and they gave us a value for it. They said it's a constant rate of 0.5, and it's measured in feet per second. So that's pretty useful. That tells us that we're going to want h in our volume equation, not r, because they gave us information about h stuff. So let's start to answer the questions. Part A says find an expression for the volume in terms of the height. So we want to just put h's only. This is going to be 1/3 pi times r squared, but instead of r, we're going to call this 1/5 of h squared times h. And let's simplify that a little bit, shall we? Because 1/5 h times 1/5 h is 1/25 h squared. And we can combine the 25 with the 3, multiplying those. And now we have an expression for the volume in terms of its height only. We don't need the radius because we know the relationship between the radius and the height. So we take that into account, and now we can just use the height, and the equation gets modified a bit. Okay, so part B, very straightforward, right? They'll either have you write the expression in terms of the height or in terms of the radius. Sometimes they'll have you do both. They'll have you go back and forth between each. Just depends on if they ask other questions. How fast is the water being poured? How fast, they're asking for ddt, is the water being poured? Now that's kind of vague, but this is referring to volume, like how much volume is being poured. And when we say how fast, we're asking like how many, like gallons per, wait a minute. It should be in feet cubed per second. This is a typo on the question. How fast in feet cubed per second is the water being poured at the exact moment when the depth of the water is 20 feet? So as you can imagine, guys, if I were filling this up with some water, the bottom part's going to fill up faster, and then it's going to take a little longer to fill up. If you've ever filled up like a cup that's kind of shaped like this, you know that that's true. Or maybe if you filled up a bottle that's shaped the other way, that's shaped a little bit more like that, you know that the water's filling up kind of slowly, but then as it gets to the top, it's like starts filling up really fast because there's not as much surface area there. So we should expect that at a certain moment, the height is, the amount of water that's being poured in there at a certain moment depends on how much height we have here, okay? So they're asking for dV dt. All right, so let's take a derivative of the volume equation. All right, they're asking how fast, which means they want ddt of something, and is the water being poured? Sorry for the misleading units there. If you got stuck based on seeing those units in feet per second and then got stuck on this problem because you thought it meant volume, but it said feet per second, so that confused you, that's my bad if that's the case. Hopefully you worked through it and understood that water being poured kind of means the volume, like how much volume, how much literal water, not in terms of height or anything, just like amount of water is being poured. All right, so let's take a derivative of this new volume equation. I should just take it from here. I guess I should take it from here in part A. If I multiply by 3, that's going to give me 1/25 pi times h squared times dh dt. And if I just plug some values in, let's do it over here. That's going to give me pi over 25. The height at that time, it says that the height or the depth of the water at that time is 20. So we're going to have 20 squared, which is 400. And then we're also going to multiply it by dh dt, which it said was 0.5 or 1/2. Right, it told us that here. The water level is increasing at a constant rate, 0.5. So we just got to plug that in. Half of 400 is 200, and 200 over 25. If you ask a kid back in the 90s, what's 200 divided by 25, they will tell you right away that is 8. That is 8 pi. Now, why am I mentioning the 90s? It's just far back enough. I think that people used to go to the arcade more. And if you have $2 and the games cost quarters, you know exactly how many games you're going to be able to play. You're going to be able to play 8 games with 200 cents, $2, and quarters of 25 each. Anyways, that's just little math tricks. So 8 pi, and this is again going to be in feet cubed per second. That's how fast the water is being poured at that moment. And whoever's pouring this is being very, very controlled. Like, this is like the most awesome bartender ever. Because what's happening here is that the height is increasing at a constant rate, which means you have to pour less at first, and then you have to be pouring more later on. So someone's very, very skilled and controlled with their pouring. That's for sure. All right, part C, final part. How fast? They're about to ask us for DDT of something. How fast is the area of the surface of the water increasing at the instant that the depth of the water is 20 feet? So we're still using h equals 20, but we're not asked about the change in the volume anymore. We're asked about the change in the surface area of the water. So what's happening there? Well, let's take a look at our diagram. It's kind of hard to tell from this side view, so let me use my three-dimensional view. As we fill up the water, right? Let's say the water level's here for now. As I fill up the water, the surface of the top, notice that it's going to become a larger circle as it fills up because the cone goes outward as it goes up, right? So the question is, how fast is the area of that circle changing? So first we need an equation to represent the area of that circle. The area is very simple. Don't overthink it. It's just pi r squared. But you might remember that we don't have our dr dt. We don't have that. So what are we supposed to do? Well, we're supposed to turn the radius into an equation with h, just like we did with the volume. We need to do sort of like part A and part B in one step. First, let's get the area in terms of the height. So A equals pi r squared for the surface area of the water, because that top surface is a circle. But then we need to change this to say pi times 1/5 of h squared, which is pi over 25 h squared. So this is the new formula for the area of this circle. Because of the proportions of the cone's height and radius, we can substitute the height, well, 1/5 of the height for the radius. Now we need to take a derivative of that, and this is going to involve only h, which is doable because we have information about h. So 2 pi over 25h, don't forget to multiply by dh dt. And now this is an expression for how fast the area is changing. Let's just plug in our given information. This is 2 pi times 20 times dh dt, which is still 0.5. We're using the same information, and that's why this is a little bit easier, because they're not having us use different information. They're having us use the same h, the same dh dt, that kind of thing. It's not incredibly difficult like you would see on an AP exam, but it is the same types of questions and the same substitution we would need to do, taking a derivative, setting up this new equation, making a substitution again. These are all the kinds of steps you'll have to do. We're just doing it with nicer, easier numbers so that I can do these things basically in my head. So we have 4 pi over 5. Pi over 5. Okay, and let's see, units usually matter. I do want to mention that as well, that on a related rates problem specifically, when they have units involved, a lot of times the questions will say, find an expression for the volume, okay, but then for part B where it says how fast, and it even says in feet cubed per second, that's their way of hinting like, hey, the units matter here. So make sure you include units. Oftentimes it will explicitly say indicate units of measure. That means if you don't do it, you're going to lose points. So in this case, this is going to be in just feet squared per second, because this is a change in area. Area is measured in feet squared, and this is happening over time per second. Yeah. So there's our answer. I mean, if you want a specific answer for 4 pi over 5, I don't know what it is. 1256. Now I'm curious. It's like 6 6.56 or something. I don't know. 6.28 or something, I think. I don't know. Anyways, that is a related rates problem. These cone problems are the tricky ones because you have to make this substitution either for R or for H. Depends on what info they give you. So read the info they give you. They tell us the rate of increase of the water level, which is H. So if they're telling you dH dt, you can kind of bet that you're going to need to change your volume expression in terms of height. And they even really guide you through that in part A. Sometimes that will be a legitimate part A question in a related rates problem. So don't think that was just like a super stupidly easy thing that wouldn't be on the exam. It would. I think that would. The other tricky part here, water being poured, it's not very explicitly clear, but I want you to learn and take a note that that means essentially the volume. Excuse the fact that it was not in the correct units. And once you take a derivative using implicit differentiation, then it just comes down to plugging in the given information. If you get stuck, then you must need to use some other equation, some other way. All right, I think that's enough blab out of me. This wraps up the non-calculator questions in this standards FRQ practice series. So I'll see you guys next time. We'll be doing some calculator problems in the void.